Hey everyone, we are Orange Origin. I'm Jonathan Tyndall, a fourth year aerospace engineering undergrad.
I'm James, the second year PhD student.
I'm Alex Avon. I'm a senior chemical engineering undergrad.
I'm Trent Murs. I'm a master's student in aerospace engineering.
I am Los Rios. I'm a master's student in aerospace engineering.
I'm Aiden Rowell. I'm a second year PhD student in Aero E with a minor in geology.
I'm Jack Maxwell. I'm a master's student in mechanical engineering.
And our industry partner is Blue Origin. Blue Origin's mission is one where it envisions a future where millions of people will live and work in space with a single-minded purpose to restore and sustain Earth. Our industry partner is Matt Jardin. He is the head of autonomy for New Glenn. And we were given a mission brief that we derived a statement to design a scalable autonomous system architecture that enables safe, repeatable, and sustainable launch operations from the lunar surface. We have three objectives. Number one is to enable rocket launches and landing operations on the lunar surface. Number two is to enable inspection and servicing of rockets on the lunar surface. And number three is to do the first two objectives autonomously.
So at the beginning of the semester, we decided to take a step back and map out the entire system that was laid out in the proposal. And so we also included the out-of-scope subsystems so that we could get a good idea of how everything would work together in a real-world lunar environment. And so we have power systems, launch and landing, inspection and servicing, transportation, propellant storage, assembly and refurbishing, and then for out-of-scope, in-situ resource utilization, lunar base, and manufacturing. And then after we mapped all those out, we did a little downscoping and decided to combine two of the subsystems, the refueling and inspecting subsystem, and to get our final current team objective to design a reusable autonomous refueling robot capable of inspecting for leaks and structural damage.
Yeah, so as we previously stated, there's two separate systems we're working on. First, the autonomous refueling, and then the autonomous inspection. So we had to look over and try to decide what exactly we wanted the system to accomplish, and we came up with some numeric parameters for us to aim for in the design. So the first one I'm going to talk about is the autonomous refueling. So this has to be able to autonomously connect to the rocket, fuel it, and then disconnect from the rocket. So just from some numeric parameters that we got from previous rockets and previous designs. So the flow rate for the liquid hydrogen, we estimate to be in the ballpark of somewhere around 300 liters per second. And for liquid oxygen, somewhere around 100 liters per second. We wanted to be able to attach to the rocket with a margin of error of around 5 degrees. We want it to be able to generate 4 bars of pressure to push the fluid into the rocket. And we want to be able to disconnect 10 seconds before launch. And then for the inspection requirements, this has the goal of autonomously inspecting the rocket for any structural damage or leaks, really anything that could potentially impact the rocket during flight. And the main systems that we're going to use to do this is thermal imaging as well as acoustic sensing.
So it's important to note that the location for our entire system will be the lunar South Pole. This image here shows the 9 different locations that NASA has mapped out for possible landing sites for Artemis 4. And so with this environment comes many challenges, including extreme temperature cycling, as well as the lack of radiation protection and abrasive lunar dust. And then we propose a 3-phased site preparation, where the first phase will be mainly human operated with autonomy thought of but not yet employed fully, and then our third phase will be fully autonomous.
One of the main issues that we could potentially face up there is the lunar dust, as Alex said. So in order to combat this, we'll be using some valves which will isolate the propellant lines and then also prevent leaks, which will provide sealing for the entire refueling operation. Up here we could just see just how bad the lunar regolith is, and then what it could potentially do to a spacesuit. We will also be using nitrogen gas to purge the entire system, and this will occur to ensure that there is no lunar dust left behind.
So moving on to ConOps, we adopted a 4-phase approach. So the launch vehicle will land on the moon and begin phase 1, where we will inspect the vehicle for structural integrity, leaks, and hazards, and conduct a systems check. That'll move us on to phase 2, where we will activate the robotic arm and engage, which we'll talk about more in the future, and engage the docking and connection. Once we have a secure connection to the launch vehicle, we can begin refueling and start the refueling process. And once fueling is complete and all system checkouts are done, we will prepare for launch, which is phase 4, and rapidly disengage the umbilical and mechanical arm, and then launch.
So on the physical side of things, we did a design trade study where we looked at 3 different system architectures to decide what we wanted to actually do to approach this problem. The first one was a fixed 2-tower robotic arm. The second one was a mobile system consisting of mobile robotics such as humanoids or rovers. And then the third was a hybrid combination of 2. So the first one, the fixed 2-tower system, it has the Pro being the simplest approach out of all. It's also largely heritage in technology and software, so it also has that benefit. And it can directly integrate into the actual launch pad infrastructure, so it can rely on things like power systems and thermal systems without having to do that itself. It does have the added con, though, of being difficult to reach certain areas on the bottom side of possible craft. The mobile system has the Pro being incredibly adaptable, so it can be used in a lot of different situations. Maybe the launch vehicle landed a bit off from the center of the launch pad, or maybe it was rotated a little bit differently from what it should have been. So you can move around to get to the proper position to maybe connect a hose or do an inspection. It also has the added benefit of being repurposable for other things around the base as well, so that's quite a huge bonus. It's really expensive to get stuff to the moon. And then cons, one of the major ones is that it's vertically challenged, sort of the opposite of the fixed tower. It has a hard time reaching things at high up places. So if there's a propellant connection high up, it might have a hard time reaching that. It also has alignment repeatability issues, and sort of the opposite of the fixed tower as well. It's got issues with power and thermal not being directly integrated into the infrastructure. And then finally, the hybrid approach, which is the one that we went with, had the Pro of being a combination of the benefits of all of the other possible solutions, but it has the added con of adding complexity, especially in situations where cooperation is required between robotics. So moving on to autonomy and navigation, how we decided to approach that. For navigation, we decided to go with, for the fixed robotic arm in particular, a robust adaptive controller. This was done in particular to deal with some of the temperature swings that might lead to joint gravity drift on the arm itself. For the mobile robotics, we decided to go with computer vision and teleoperation / virtual training for informed path planning for the mobile robotics. Inspection, we also use computer vision combined with convolutional neural networks for leak detection. Convolutional neural networks are standard for object detection, which is why we went with that. And then we also decided to use variational autoencoders for structural damage detection. Variational autoencoders are good at detecting patterns and noisy, weakly labeled data, which is why we went with that, because structural damage is hard to define beforehand. And also, an unsupervised approach allows us to deal with failure modes that are hard to predict beforehand. And here we've got a dynamic and control model for the robotic arm. It's preliminary at best. It's a 6-degree of freedom manipulator. The controller is, like I mentioned before, robust adaptive, and I didn't mention before, but it's got memory modification. The trajectory that you see there on the screen is not anyone in particular. It's just kind of sort of to stress test the model, which is why it looks funky and crazy. And on the right here, you've got pictures of the desired path for each joint, which is the dashed line, and the actual path that was taken by the controller. And you can see it's pretty much one-to-one for every joint, except for joint 3 and joint 4. What you're seeing in joint 3 and 4 is a little bit of error that occurs in the dwell of where the joint is acting as an elbow.
For the system level autonomy, we are mainly focused on the logistics, schedule, and resource allocation. In the later stage of lunar facility construction, coordinates the complexity of the multiple spacecraft and manage the resource logistics to achieve the mission goal will be an inevitable challenge problem. Our solution is to develop an autonomous resource allocation system driven by AI, which can automatically to generate the logistics schedule to replace the human engineers. This is our solution. We developed a software called the Eldoras, which is a reinforced learning algorithm which can generate the schedule based on the mission goal and operation logic of each part of a lunar facility and the physical constraint based on the conditional expectation precisely calculated based on the multiple physical simulation. Our AI schedule will guarantee the adaptive decision making in our space mission and achieve the optimization of the resource usage and finally improve the overall mission efficacy. As you can see in the animation in the slides, we have the early feasibility demo when a lunar lander land on random position nearby our lunar base. Our algorithm can automatically to schedule to assign a lunar rover to pick up the lunar lander and put them to the lunar base to do refueling and then place it in at a suitable position and finally launch. Our software also have capability to do the estimation of the time usage and the resource consumption and quantify the uncertainty based on the identical repeat experiment and testing. Our algorithm have given calculate the resource usage number as shown on the table. And the detailed logic is as shown in the action type table in the right.
So for the autonomous inspection of these launch vehicles, there's a few kinds of sensors that we want to implement. For leak detection, we plan to use thermal imaging. So a thermal imaging camera can easily detect vaporized propellant leaking from the vehicle, and we can use a computer vision model to distinguish between actual leaks and regular venting. In situations where thermal imaging might not be appropriate or might be unusable, we can use a simple gas sensor. For structural fault detection, we plan to use vibrational testing. So this will include attaching a vibration source to the component of interest, measuring the vibration response using laser Doppler vibrometry, and any differences between the measured and expected responses will indicate some sort of structural defect.
So moving on to our prototype, we wanted to validate our thermal imaging capabilities. So we spent a few weeks working on a setup to prove two things. Number one, that we could detect a leak using a thermal camera. And then number two, could we train an AI model to do that for us? So we initially started with a helium tank and as the leakage gas, and then dry ice and a pipe. So we controlled the flow rate by drilling holes into the pipe and tested if we could visualize the leaks using a thermal camera. So we ended up initially having quite a lot of issues with it because helium, as it turns out, has very low emissivity in the infrared wavelength. So after much troubleshooting, we ended up trying to use solid carbon dioxide or dry ice instead, and then we used the helium as an ullage gas. So we essentially pushed out the carbon dioxide, and then as it was being pushed out of the pipe, we were able to image the change in temperature using a thermal camera. So as we can see here, we have two GIFs on the right. Number one is the leak detection video captured, and then we also applied a fast Fourier transform to simply just extract out the image better so that we could feed it into our algorithm.
In the algorithm part, there we have two significance in two parts. One is data pre-processing, the second is machine learning model training. For data pre-processing part, we assume that the fuel leakage is a high energy event and it's possible to be captured in specific frequency band power. So we use fast Fourier transform to do the data pre-processing, and we also developed a software with the GUI to do all the processing on site. And based on the test results, we have significant displays where is the gas leakage happening, as shown in the figures. And in the model side, we choose a lightweight multi-layer perceptron machine learning models, and we train the model in 130 video samples, and we do the hyperparameter fine-tuning using the validation video with the 33 sample guided by generic algorithm, and the algorithm finally finds that using 464 as the number of hidden layer dimension have given us the optimal result. And we finally testing our model under the 70 samples, and our benchmarking results show that our model have reached 98% accuracy. This is a very promising result, which means that it have capability to download in the edge device to detect the gas leakage in real time.
For autonomous refueling, there's a few more sensors that we want to implement. For the umbilical connection, we can use a trained computer vision model. This will ensure accurate propellant port location and connection. And we can also, of course, use simple clamps and O-rings to ensure no propellant leakage. For the actual propellant monitoring, we can use long short-term memory. So this is a kind of neural network that excels at recognizing patterns in data. So this will be able to detect any sorts of anomalies in the propellant flow, which means that it can halt the system if it needs to. And beyond this class, we would continue to develop subsystem prototypes to test our ideas. We would, of course, seek funding and sponsorships. We would further investigate all sorts of aspects of the lunar launch system, and we would conduct more beneficiary interviews.
Thank you guys, that is our presentation. Do we have any questions?
Matt, the floor is yours.
Hey, can you guys hear me?
We can hear
Yeah.
you.
Awesome. I heard you guys well, too. You did a good job in presenting. I was able to hear pretty clearly through all of that. Overall, just fantastic. I'm very impressed with the work you've done as a team. From the very beginning, I've seen good, steady progress. I was pretty much not worried about you from the beginning. You seemed to understand the problem. You understood that this is a huge problem. And you did a good job to narrow your scope, and you found some of the really critical issues that there will be with operations from the moon. Showed good judgment on your part. And I really like, as we got towards the end here, you slid in some things there that I didn't even know to expect. So I really love the experimentation you did with the leak detection. I like where you got with the LDORAS. Your communication of what that was doing was much better. You set the stage for that really well and helped understand, what optimization problem you were looking to solve there. You're using very appropriate techniques to solve that problem. I really like the machine learning approach for autonomous refueling that you talked about there, and monitoring the various temperatures and pressures and detecting faults. Overall, the presentation looked great. As with what Rashid said about the prior presentation, I didn't find anything too distracting on your slides. They had good information content, not too dense, not too light. So overall, just fantastic. I've seen you guys have refined it quite a bit. I don't have a lot of critical feedback